involves using existing, relatively communication powerful mechanisms to communicate.
Everyone, I'm Muninder Singh, Professor of Computer Science at NC State, and it's my distinct honor and pleasure to be hosting Professor Victor Lesser today. Vic was a distinguished professor of computer science at UMass Amherst. He retired to emeritus status in June of this year, and but he's continuing to be an active researcher. Over the years, he's advised 36 PhD students. I note here that he's won a large number of best paper awards, but in addition, he's a founding fellow of AAAI and IEEE fellow. He was the founding president of the International Foundation of Autonomous Agents and Multi-Agent Systems. He's received outstanding research and teaching awards, and he received the UMass Chancellor's Award for outstanding accomplishments in research and creative activity. And he was also the recipient of the 2009 HCI Research Excellence Award. And one thing that the students here might find interesting is that there's a dissertation award called the Victor E. Dissertation Award given by the International Foundation for Autonomous Agents and Multi-Agent Systems, which was named in his honor. So you usually meet people who are recipients of awards, but here you meet a person who has an award named after him. And it's targeted at students, and I hope you guys all aspire to earn that award someday. So with that, let me have everyone welcome Vic to the talk.
So today I'm going to give a talk about a project that I've been involved with. It's a very large project. It's a 10-year effort as part of an NSF Engineering Research Center at UMass. And its effort was to design a new class of radars for detecting severe weather phenomena. And what has been so rewarding for me is that multi-agent technology, especially the cooperative stuff, has been a very exciting and intellectually challenging and productive research area, but there are not that many real-world applications or real-world applications that people will talk about of this technology. So it's a nice thing to be able to say that here is a really important application. It's a fielded system. It's got a lot of national publicity. And we have used multi-agent system technology and also agent technology in building the system. And at least two of the aspects of the talk today are in the fielded system that runs in Oklahoma that's recognizing tornadoes. So that's the context. I want to make sure that I give appropriate due credit. This system is a large research effort that involves people at UMass, the electrical engineering department, the computer science department, and then people at Oklahoma University and Colorado State, and also University of Puerto Rico. So it's been a wonderful activity that have gotten a lot of students involved. And I'm not an NSF person, but I feel for the projects I've seen, large-scale projects, this is one of the more successful. So it's been a really rewarding effort. And now the project is coming to the end of its 10-year cycle, and it's starting to move into other application areas. So, but this sort of is a good view of what it's doing or what it's done for the first 7 or 8 years. And so, why isn't it going? All right, great. So the picture, it's not, I want to go back. All right. The picture you're seeing, is there a sticky? All right, now it's going to go again. All right, all right. That was a picture of a tornado. Right, and it went quickly, and tornadoes go quickly. So the question is, how does multi-agent technology apply to detecting tornadoes quickly? And I'd like to give some acknowledgments. The slide doesn't, are all the slides going to be like this? Mike Zink, who's the deputy director of CASA, which is the umbrella organization that is responsible for this and one of the chief architects of this system, and David Westbrook, who was a former student of mine, who's also one of the chief software developers who worked closely with us to get our software into this test bed. And I really appreciate all the work that they helped us in actually getting that software in there. And also, some of the introductory slides are from Professor Zink in terms of the overall architecture of the system. And I wanted to make just a point that is interesting to people is that when you're building a big system, there's the real system, but you need simulators. You need to be able to do experimental work when you don't have the real system to use. And this project has been very successful because there was a lot of attention to building simulators, and there are a number of different simulators at different levels of detail, that the code could be debugged when the hardware wasn't even available. And for my work, we were able to use the simulator to look to see larger configurations and what would happen with the system in larger configurations. And what was surprising to me is the code that we developed for our simulators just went in lock, stock, and barrel right into the regular system. So that was I didn't expect that to happen, but that's very nice, and it's really a nice methodology. So when you have these big projects, use of simulators and software engineering is really an important thing if they're going to be successful. All right. Excuse me. Not responding. Okay. So the lecture is going to be broken up into 4 parts. What I'm going to first do is give you an overview of the architecture of the distributed collaborative adaptive sensing system. Then I'm going to talk about some multi-agent issues involved in scaling up this system to large configurations of radars. I'm going to talk about 3 issues. One is distributed coordination, coordination of radar scheduling. It has to be done in real time. Distributed meta-level control, where we're starting to adapt the system dynamically to the emerging scenarios in terms of setting different system parameters. So the coordination is adapting to the weather phenomena, but also this is a more global adaptation, saying as the weather conditions change and the types of storms you have, you may want to set parameters a little differently in the system. And the final thing is talking about going from a reactive control approach where you're scheduling on each cycle to looking down the future and seeing activities and tasks as more multi-step activities and beginning to think about scheduling and coordination from that perspective. So those are the 3 different topics I'm going to talk about. Our current system, and please don't ask, by the way, you can ask questions, interrupt me at any time. I will try to do the best I can to answer those questions. This is an area that I'm not super expert on, but I'll try to give you a good feeling for it. The current weather forecasting system in the US has 158 large-scale radars that basically sit and spin around 24 hours a day and pushing that data to the weather forecasters, the emergency forecasters, whatever. Now, because they are large radars, they cover a large area, notice that if you have the curvature of Earth, you're not going to capture, where's my, okay, excuse me. Notice that the radar goes out, and this area, this gap, you're not seeing weather phenomena in the first 1,000 meters. And you actually have 72% of the troposphere below 1 kilometer not being observed. And there are also valleys in California that can't be seen and coastal rain issues. So these systems, even though they're very important and effective, are limited in their coverage. And there is important things going on at this area that if we could detect them, we could do better forecasting. And that's the overall goal of the project. And the goal that was set up 10 years ago was to be able to track tornadoes down the street in real time. So you really want to get a picture of the tornado and its track. And this is from a real system. So in fact, it succeeded in meeting its goal. And it does, there has been some data, comparisons of what this system did versus the national weather, and we do it more precise and quicker. So I mean, it's not, there's a 4-node configuration of these radars in Oklahoma in the Tornado Alley, and we do get some tornadoes in there, so and we haven't lost any of the radars yet, but we have been able to pick up radars and interesting events.
Do radars have call signs? Is that
What?
Do radars have call signs? Is that what those 4-letter things are?
You know, I don't know. What do you think?
Well, they are transmitters, so maybe.
So maybe that's the case. Maybe that's, all right. Question to, I did not look at the slides closely. All right. Is it going on to the next one? All right, come on, where is it? There we go. So, sorry about this. So, the distributed collaborative approach is to have radars that are short-range radars that cover maybe 30 kilometers, that hug the curvature of the Earth in their signals, and that they overlap. They're densely overlapping so that multiple radars can look at the same area. And that's very important because there's ways of detecting things by having multiple radars point at the same area. You can see phenomena that you can't see from only a single radar. And here you have what we're going to call the MCC, which is the control unit for a number of these radars. And my work has been in basically the scheduling involved in this local unit of these radars, because these have to be scheduled on a real-time basis, but also what happens when you scale this up and you have a lot of these centers that then need to coordinate together. So it's finer spatial resolution, and because these radars are adaptive, what do I mean by adaptive? Is it's no longer a push system, it's also a pull system that we can tell the radars where to focus their time. So if there's nothing interesting in that area, why spend time scanning there on every cycle? Maybe you want to scan every 5 cycles because something may occur, but you don't have to do it every cycle. So I can spend more time just focusing right over in the exit where there's something interesting happening. The more time you spend scanning in an area, the higher the resolution, the better predictions you can make. So you have that, and let's see. So I think those are the main points. And we are responsive to multiple end-user needs. So if users decide they want to focus, even though the system is not seeing anything in the area, someone is interested in really tracking that area closely for whatever reason. Maybe they have a ground spotter that's seen something in that area, and they want to go into that area. We can have the system focus in that area and dynamically set the priorities to go into that area. Yeah?
So does this network of densely packed radars exist, or you're?
Yes.
Okay,
There's the system, the picture I showed you is the real system.
okay.
It's a 4-node configuration, and the data is real. And in fact, at the end of the thing, I'll show you a trace.
Okay.
So so this is the basic, this is a picture of the 4 radars in Oklahoma. And you have this process where they transmit the data. The data is then done using meteorological detection algorithms that are running in real time. We analyze that data. We then put it on a Blackboard where we take this moment data from the different radars, integrate it into the Blackboard, try to recognize interesting groups of events, make predictions about where those groups of events will be moving in the next cycle, then decide what tasks should be done in the next cycle in terms of which of these are more interesting phenomena and how much we should scan them. So you have the raw data, generation of features, generating of tasks, and then an optimization that generates a scan strategy for those radars saying, focus in this area for this amount of time. And that's the basic architecture. Do people understand that? Is that clear? Fairly simple. But in fact, I want to say that this is not, there are not that many systems that really involve this closed loop, adaptive radar systems. And I believe that you're going to see a lot more of these types of systems where sensors will be parameterized, they'll be able to be adapted, you're going to have processing of the data and the dynamic integration of things. And this is a vision we've had for 30 years, and now we're starting to see it. We built the system for DARPA in a very simple way using this type of technology 10 years ago. But there aren't too many systems that really have this closed loop sensing and also the distributed collaborative nature. Yes?
What's the time frame of each cycle?
All right. It started out at 40 seconds, and it's now 60 seconds. And I'll explain why later on. And we can push it down further if we want to. And it's a political question. And again, I have to be careful about what I'm saying because this is going on YouTube. So this is a picture from the real system. Here you see detections of interesting weather phenomena. Then you have this grouping of them into tasks of phenomena that are similar in character that you want to scan with the same type of parameters. And you're forming polygons. And then you're making choices among all the activity. You're making predictions about where they're going to be. And then you're deciding what to scan and which radar should scan what. So notice the radars are, this radar is only scanning in this area, this is scanning in this area, this is scanning in this area, and this is scanning in that area. So it's a selective scanning thing that's dynamically chosen. And obviously, if there are a lot of phenomena, you may not be able to scan everything. And that is where the optimization problem comes in. The other optimization problem that we'll see in a second is that you may want to have multiple radars scanning in the same area in order to get better resolution and do some different type of processing on the data given the two perspectives. Yes?
Right now you have two radars scanning the same area more or less.
Right.
And that's by design.
Yes,
right?
that's by design. Exactly.
So when they're focused, they're not doing 360s?
No, these are not doing 360s.
Don't they wear out quickly?
I don't know. That's a, I don't, you're getting into things I know out of my level of competence. But I want to say that they are moving to an all-electronic system.
Ah, okay.
And they've done the first part where I believe they have the electronics,
So
the
towards
beam
synthesi-
focusing all
synthetic
electronic,
aperture?
but they're still doing some movement.
Okay.
And then the next step will be a totally digital system.
Wouldn't they just rotate and the 3/4 of the registers don't cares, right?
No, but what
No,
he's
40,
saying, what he
20
was
seconds.
saying is there's a cost because it has to, it's going like this,
If you
rather
ha-
than,
I ask, it's not going around 360 during the 40 seconds it's
right.
focusing.
It's going back and
Oh,
forth.
it's-
See, it's doing this sweep horizontally, tilt up.
Okay, yeah.
That's the basic thing, and so it's not sweeping the whole thing. And yes, that was the most difficult part of designing the radars, is to get the mechanics right,
Okay.
that they do it. And they haven't talked about your problem,
Okay, okay.
but that doesn't say it doesn't exist.
Yeah, yeah, yeah.
All right. Very nice. So, I mean, we worked on the optimization in the local MCC, but the multi-agent system technology is really the scaling up. And in fact, we have actually run these algorithms on the real test bed where we've either worked with clusters with 2 radars or each radar having its own controller and testing out all the distributed algorithms in that framework. So I want to say that this is a real live system, real live application, and tested in a real application. And here is the issue on the multi-agent. So here you have MCCs, each one having a group of radars associated with it. But notice that there isn't a clear demarcation between the radars in MCC0 and MCC3. They're overlapping again. So you then have the problem of, here's an example where radar 1 in MCC-A has these 3 phenomena that it's seen. In MCC-B, there are 3 phenomena also, 1 in the overlapping area. So in a simple way, there are 7 different configurations that you would want to, you could possibly see. John, there could be a lot more.
Yeah, yeah.
You could scan here, scan here, scan here, and skip those places. I don't think they did it.
Okay.
I suspect because of some issues
Yeah.
in there. But we could handle that. It increases the combinatorics. So the question is, what configuration here and what configuration here do you choose to get the maximum utility that's associated with scanning this? So each task has a utility or importance in terms of how much effort you're going to put in there. So you could scan this area completely and you get a very high credibility for this, or scan it like this where you get some credibility for each of these 2 tasks. So it's that type of decision that we have to make. We do a utility optimization algorithm to make that decision. Well, obviously, if you have this radar and this one, it's making the optimization for these radars. This is making the optimization for R2 given the context of the other radars. Well, you're not taking into consideration that R1 may be scanning this and R2 may be scanning it and may not be a pinpointing task. It means only one of them should do it. So you're wasting resources. Or this is an important task and both need to do it. So you need to make sure that you have a schedule that both does it. And that's the distributed coordination problem. So it integrates scheduling, local scheduling, and coordination of activities. So what I should say is that this is I'm going to talk first. I'm going to talk about our first approach at doing this problem, and then a more general approach that we just implemented to doing it. And one of the exciting things about where multi-agent systems has gone over my lifetime is going from heuristic approaches to thinking about the issues involved in multi-agent systems from a more formal perspective. And over the last 5 to 10 years, the idea of distributed, decentralized, partially observable Markov decision processes to think about sequential decision making in a multi-agent system has really become the way to think about problems, at least as a baseline, to think about problems, and also distributed constraint optimization as a way of thinking about single-shot decisions is the way. So what I'm going to do is talk about our original approach and then talking about trying to reformulate this problem in a more general way in terms of a general distributed constraint optimization problem, and then using an approximate approach to do it. So where we are now in the field is, is that there are some very nice formalisms, and for many problems, to get the optimal solution or to get a bounded optimal solution are very hard to get algorithms that perform in real time. So we have to go to approximate algorithms. And so that's what we're going to talk about. So the original approach involved 3 stages, 1 or 4 stages. An initial stage where the different MCCs transmitted some data about what was in the shared region, so that it was possible that one agent, because of its local view, didn't see something while another did in the shared region. So we want to get that consistent view about the shared regions. Then each of the agents makes a local optimization, not assuming anything about what the other agents, its neighbors, are doing. Right. The next step is the agents exchange this local optimization, especially what they're doing in the shared region. So I don't need to tell you what I'm doing in my local region, in the shared region. Okay. And I sort of say, if you, now you've told me before what you're going to do in your local region or in that thing. So I'm saying if I know that you're going to scan in that region, then I can improve the utility of my current schedule by, for instance, not scanning in that region. So I'm going to get a gain of utility. And I'm going to tell my neighbors I'm going to get a gain of utility. We're all going to do this. Then we're going to choose the agent that has the best gain in utility. And we're going to be a little more clever and say, even though you've changed, you haven't changed the assumption that I am using, so there's possible that multiple people can change simultaneously. So, and then we're going to repeat this cycle for a number of things and monotonically increasing improvement in the thing. So local optimization phase, sharing some information about the local optimization and what the other neighbors are doing, and then making a utility calculation, choosing who best to make a change and incrementally improving the system. And we use an anytime genetic search algorithm to do the local optimization. And for real-time things, you can reduce the search space by limiting the set of possible scan strategies, the size of the wedge, etc. So we're dynamically doing this to conform to the real-time things where we have about 20 seconds to make that decision.
Was there a typical number of iterations that you need to go through?
Well, we time it to 5.
Yeah, okay.
Okay, so this is just an example. Here, P means a pinpointing task. but you get a lot of utility for both of them doing it. So the initial configuration is this agent is scanning in this one, this is scanning in this one, and this is scanning in this one. Can anyone see why that's not good? All right. Well, two things. One, two people are scanning here, and it's not a pinpointing task. And only one person is scanning in this pinpointing task, and you're not going to get a very good utility with only one looking at this thing. Yeah?
What's the significance of the black arrows?
Well, that's information can be transmitted. So, based on what has been seen, this agent is saying that if I know that you're going to scan in this area, you are scanning in this area, and you're going to continue, I'm going to change where I scan, and I'll scan here, and I'm going to get a big utility hit. And this one is going to say, you know, if I'm going to get a utility gain if you scan in that area. And what we're going to do in this case is to simplify it. Potentially we could do both, but we're going to just do, at this point, just one. So there's an agreement selection process. We obviously see that 5 is the best one. And it leads to this schedule. And we do it again. And this time you obviously see that we're going to make this change here. Come on, come on. Slow. Okay. So it's going to put all its effort here to get the highest rating on this important task. This is going to do this task, and this task is not going to be done. So that's an example of the optimization, and it works fairly well. Not badly.
So if the blue one expanded its field, wouldn't that be better, or would the cost?
Well, what would be the thing if it scanned this whole area? Okay, let's say that would be expanding the thing. I was talking with John about the possibility of scanning this area and scanning this area, and that may be the hardware issue that's not easy to do in the hardware, but I'm not sure about that, what the reason was. But look at, if we move this blue arrow here and we say that it's scanning over this time, how much time is it spending here and how much time is it spending scanning here? Look at all this time. There's nothing interesting here. So it's spending 5 seconds here and 5 seconds here, rather than spending 40 seconds in this area. And that's going to get a much better view on this important task. So that's the analysis. All right, I better move quickly. I'm going too slowly. There's the initial configuration. All right. So it doesn't. It's a hill climbing algorithm, anytime algorithm, but not guaranteed to. It's guaranteed to converge, but to a local optimum rather than not. So the question that I had was, I was very interested in these new class of distributed constraint optimization algorithms. Could we formulate this whole problem rather than having a two-phase system where there was a local optimization calculation and then the negotiation? Could we think of it totally as a distributed constraint optimization problem? And then the question you'll see is that the performance wasn't so great. It was good, but not. There were problems with it in terms of resources, time, and amount of communication. And we went to a DCAS. We exploited the hardware technology, the hardware topology, where you had a number of radars within an MCC, and we adapted the algorithm based on that. So this is the optimization problem. You're wanting to find the scan schedules for the radars to optimize the sum of these functions, and each function is associated with a weather phenomena. So what you have here is, this is the list of radars that are able to see this weather phenomena. And so then the function is trying to, will compute a value based on the scan, particular values you've chosen for the scan schedules for each of the variables, each of the radars that can see that thing. And then that becomes a value for here, and you're trying to maximize that. That's the constraint optimization problem. Notice that everything is not a local phase and a non-local phase. So we're thinking of the whole problem as an integrated view. And I won't go into this, but what we have to do in having each cluster have part of the problem, we have to make sure that the same phenomena is not represented in both things, because we're really having this network, which is then distributed to each of the MCCs. And it's a simple calculation. The max sum is an algorithm for distributed constraint optimization that's gotten a lot of play in our field. It's coming out of Nick Jennings' lab at Southampton. He's actually applied it to real problems also, and he's gotten very good results. And I was on the advisory board for his group. And I said, OK, let me apply it to my problem. And basically, what it will do is if this network has certain properties, like there are no cycles, you get an optimal solution. This has cycles. So what it is doing a calculation where you send a message from each function node to the variable nodes connected to it, and involves an optimization of saying for each particular value of that variable, what would be the best value I can get. And it's taking into account messages it's received from other variables about what they've optimized. And it's a nice algorithm that does very well. And really, I was basically surprised that it actually does better in all the cases in terms of getting utility. Slightly better. This is the negotiation approach. This is the max sum. In this case, this one here is an optimal algorithm called DPOP that doesn't extend very well for larger numbers of radars. We couldn't run it. But it does give you a sense that we're getting very close, within 5% of the utility of the optimal solution. And the white line is a centralized approach that uses that local optimization algorithm on the whole network. So we're doing very well. Here we start to have problems. If you look at the time is about 100% longer to take to do it. And look at communication, using a lot more message bandwidth, which in a multi-agent system, at least for some applications, is very serious. All right, so that's a problem with that approach. And if you have more dense number of phenomena per radar, you have a lot of weather phenomena, you really start to see a severe bottleneck in terms of communication. And the question is, how could we, there are a lot of nice advantages of using a formal approach. How could we speed it up to make it competitive? And in some sense, we're going to use the idea that we had with the first approach. We had a local optimization phase and then a negotiation phase. So we're going to do something similar. So we're going to do a computation on that local network of the radars and the phenomena within one MCC. We're going to spend some time doing that message passing only within that local MCC. So there's going to be no communication across processors using bandwidth. And then, so we're going to spend a certain number of cycles doing local things, and then we're going to send a message. So we're going to reduce the number of messages in that way. Now, look at this. No change in the utility. We're getting the same utility. We're getting improvement in time. So we're getting speeding up of the application. And significant reduction in bandwidth as a result. Now, one of the things that's very interesting, and this sometimes you get from peer review, saying, well, someone said, what if you just throw out messages? The system does surprisingly well when you just throw out messages. If you go back, you'll see the utility was maybe 5 or 10% lower. But just the action of that algorithm, the iterative nature of the algorithm, and the fact that as you go down iterations, things don't change that much from iteration to iteration. And so there's some interesting issue of just throwing out random amounts of information. These algorithms perform well. And in fact, it goes back to my original work in multi-agent systems in 1978 when I did this distributed hearsay 2 experiment where we just threw out randomly 50% of the messages in the system could self-correct. So it's an interesting view of looking at these algorithms that have this self-correcting character to them. And it's really a surprising nature. And I don't think we think about computational algorithms enough in that way of the self-correcting character. And the question is, can we bound what's going to happen, or just we have to do it empirically on faith? And that's potentially the real problem is, can we get bounds on what's the effect of this inconsistency?
Well, how valuable would it be to just have something which doesn't look at the data at all and says if it's March in Oklahoma, it's a tornado?
That's unfair. That's unfair. So do I have 15 minutes or less?
Yes.
15 minutes or less?
No, I think you have.
No, 15 minutes.
You have 15 minutes. Yeah.
15 minutes. Okay, great. All right. So I think it's really an interesting thing to formulate these problems as an optimization problem, these coordination problems as an optimization problem, distributed optimization, use approximate algorithms. I think that's really a win. But we have to tailor it. And so I think this is the direction the field will go in. At least we've had a lot of good experience.
What size of the problems are you actually talking about? Variables? You're talking about the binary variables, I presume?
Well, you know, I was surprised. No, the variables aren't binary because they're radar schedules.
Yes, but they're encoded into, I mean, if
Yes.
it's a genetic algorithm, that it means you probably have a string.
Well,
How long is that string?
it's really interesting. We're doing some work on improving that maximization process that's going on in the message passing algorithm. And I was shocked that we're getting lists of 40,000 values that we need to sort for each cycle. So it's non-trivial. The problem is non-trivial
Okay.
in that sense. So we're doing new approaches to trying to speed up this process, to not send all the information on every cycle, and so forth. And really, the idea is you look at these constraint optimization problems, and we had a hardware structure that imposed a decomposition of the thing which was relatively nearly decomposable, and that you got a lot of action within the MCC and then looser connections across. And the question is, can you use this idea more generally in these problems to not transmit information everywhere that's you're connected to, but limit it to a region and then expand that region in terms from time to time. So it's not a great idea, not a new idea, but I think it's an interesting idea to think about how to improve the efficiency of these algorithms, hopefully without losing too much. All right. So let me move very quickly. It turns out that this heartbeat can be changed. And the question is, how much time do you want to spend doing an optimization, collecting data before you make a decision about what the next scan cycle is? So if it's a longer cycle, you're collecting more data, you're having more resolution, you're having a better view of the phenomena, you can make better predictions about what's going to happen in the future. But, so you could obviously make it as long as you want, but things are changing. So if you hold it too long, the phenomena won't be there any longer. Now, so if the weather is moving very quickly, you want to get the heartbeat shorter, while you can have a longer heartbeat and get better data and be more efficient in your scanning. So it's an interesting trade-off. And the question is, can you adapt the system dynamically to the changing weather conditions? So there are two changes we're going to talk about. One is, can you change the basic heartbeat? We want to dynamically change the heartbeat. And we would like to change the task interdependency among the MCCs. So potentially, if there's a lot of interaction at the boundaries between MCCs, then you're going to spend more time coordinating. You have to cross that boundary more often to get a better solution. So, and if you're only having a fixed number of cycles, you're going to get less than, not as good a solution if there's a lot of things in the boundary with the fixed cycles. So, what can we do? Obviously, we can change the heartbeat. So we can scrunch this down. And we'll add a new phase that's going to make a decision about whether to adapt the heartbeat. The other thing we can do in a limited way is say that certain radars can also transmit their information to other MCCs without too much penalty. So do we want to change where the radar is sending its data to in order to speed up the optimizations by localizing the phenomena that are integrated in the same MCC? And that's what we're going to do. And let me quickly go through this. So that's an example of reorganization. So this is an example of reorganization where there's a lot of shared data between these two, and there's a lot of communication among these MCCs because of that. But here, we can break that communication by moving R3 to R4 and doing some other reorganizations of other things. So we have to do two things. One is, how do we develop policies about how to do this adaptation? And if they're local policies for each agent, what happens? Could they be in conflict? And it turns out they can be in conflict. So two agents may want to move all those radars into the same one agent, which then overloads that agent with too many radars to process data. So you can get into conflicts. And so what we're doing is learning a stochastic policy based on the state of the world. An agent is making a decision to do a certain meta-level action. And we're doing offline learning based on different types of scenarios of the weather phenomena and what's the best response to do in that case. And it's a stochastic policy that, just to give you some heads up, we found that stochastic policies are really good in a multi-agent context. that you need a certain amount of randomness that you get better performance that way. Just to say that the state space could be very, very large if we have a lot of detailed information. We can really cut it down to not so large a state space by making a lot of abstractions and using a little bit of information from other agents. So the abstraction in a local agent is something about, very little bit about what it's doing and what its relationship is with other agents in terms of correlations, and then also what the other agents that are surrounding it are in terms of its interaction with it. And so, I mean, it obviously goes up significantly if there are more than two neighbors. And we develop rules to deal with this conflicts that occur from the meta-level actions of different MCCs not being coordinated. So we tend to get about 10% improvement as a result of these reorganizations, which is non-trivial. And we actually get some further increase when we have this second stage of resolution where the agents try to avoid conflicts. But the algorithms we have are very simple, and in fact, they don't do too well as we have networks of conflicts. You know, that I can maybe resolve a conflict between us three, but if there's the surrounding neighbors that have conflicts with you, it just breaks down, doesn't do very well. We want to solve that problem. But that's just an example of, so here we're saying, we've talked about distributed coordination, formalizing it, the need for meta-level control that can be helpful in things changing, dynamically changing system parameters. And next I want to talk about thinking about optimization, not from a single cycle, but from a multi-step optimization approach. And this is, again, another fielded application. If you look at who's using this data, there are a lot of different people. There's the Weather Service, there are researchers, there's emergency managers, there are other people who are using this data, and they all have different criteria. And you talked about Brenda. That's what Brenda is doing, I think, a thesis on how to integrate those different perspectives. The issue that I perceived is that they did a lot of work in the system in order to make this happen. They changed the cycle from 40 seconds to 60 seconds, so every cycle has a 20-second spin around, because some of the people just would not accept the fact that they couldn't see it with some level of resolution. Because the system wouldn't guarantee that within 5 minutes they would get a full scan of the whole region. So you want to start to think about these activities, these goals of the system, as not being a single cycle, but rather tracking this phenomena, the slow speed phenomena, within a certain level of accuracy, because it's not going to change. You don't need to do it everything. You need to do it every 2 or 3 cycles. Or you need to do a complete scan. You need to have enough data to generate a complete view every 5 minutes. So these are more long-term goals that don't fit in well with the reactive control. You've got to play a lot of games, and it isn't perfect. But it's much better to think about these as goals and having these multi-step goals that can be satisfied in different ways, and then thinking of the scheduling problem in that way. And basically, and I don't think that I need to get into a lot of detail. I think I've said that. And what we also have to do about this, which turned out to be very nice that we didn't do it, but they had been developing it itself, is more long-term predictions, because there was an immediate prediction in the system about 1 cycle ahead. Now they're doing 5-minute projections forward. And we could use those projections to actually say that there would be certain weather phenomena that would be occurring down in cycle 3 or 4 that we needed to plan out to worry about. So we were actually projecting the future ahead, and it wasn't just the tasks that we saw now, but we could potentially think that we could see other tasks down the road, and we did our scheduling based on that. So you have a continuous time optimization thing. Obviously, you could do it forever, but you fix a certain horizon, and it could be dynamic, and you're then constantly on every cycle pushing the horizon for one cycle. And that's the basic algorithm. And one of my students was very, well, there are goals. Okay, so let me finish quickly. What we could do is actually very clever in mapping the genetic algorithm to have genes that represented sequences of actions over multiple cycles. And so we're searching on policies in the genetic algorithm, and it actually works quite well, to my surprise. And we need to update the goals after each heartbeat to say what is the result of what's happened. And there may be new goals that modify existing goals to reflect partial satisfactions and changes in predicted storm movement. To say this, probably the right thing is to say what's the highest one, and that's this one, the yellow, the green one, and that's the distributed negotiation one using this technique. And they're all normalized with a centralized view of a single shot reactive. So we are getting, in this case, 20% improvement in the overall utility being generated by the system. And what I'm going to do, and sort of just let the system run for a minute or two, is show you the real system running. And what people have done is the experts have looked at it and said, it's doing a better job with the goal. So the first stuff was simulation stuff. This is the real system. You don't have exact measurements because we can't replay so it's really done on 2 different time shots of the data. Okay, now there is some way to start this. Okay. Come on. Is it started? Well, there's my future work, but that's not the slide I wanted. So that's what you see as the system dynamically adapting the scans, and that's the old approach and the new approach. But that's what the real system. That's data from the real system, and it's performing. I can't make out why it's doing better with the new system than the old system, but I've been told. So hopefully believe it. Okay, sorry about that. All right, that's the conclusion of that. But so hopefully, wrapping up, hopefully I've shown you that we really can use agent technology in a real problem that has social utility and that it really affects the performance of a real application, is key to a real application. So that was what I was wanting to tell you. I don't think there are very deep ideas in the technologies that I'm talking about, but it's just interesting that it it can be applied to a real problem, and that I really think that more and more as we lead to decentralized systems, to more open systems, that my hope is that multi-agent system technology will really take its place as an important technology in how we build these systems. So that's the overall message, and I think that there continue to be a lot of interesting research problems, and it's very nice for my group to have this simulator that we can really explore new things and know that we're pretty close to what an actual system would do. All right. Thank you, and I will take any questions. And I don't think I said anything that I should be ashamed of in YouTube land out there. So, okay.
Remote sites.
Someone got to ask a question.
Remote sites.
Both sites. No question? Okay. Yeah?
Part of the reason I ask about the dense packing is I was wondering, that's only in high-risk areas, or that's across the whole country now?
I mean, where, how is it going to be built out?
Well,
I don't, to be honest, all I know is that they're going, I don't know whether I told you, they're moving the test bed from Oklahoma to Houston now, and they're going to build it out to 8 or 9 things, and they're going to use it for not tornado, but for flooding,
okay.
where you have a lot of micro flooding, and this system has the ability to look at rain patterns and get very good data on rain patterns. And so that's an interesting application because there's a lot of micro flooding in that area, and being able to warn people is very important, especially for the hospitals and things like that.
I'm from Houston, and
So you know what I'm talking about. So there's it's honest.
yes.
And the other thing is that this is very good at detecting wind shear. So there may be other applications. So there's a whole host of applications that are being thought about for this radar, for this system.
Maybe this is a silly question, but we already
Nothing
have
is silly.
a dense network of cell towers. And can you get any information about the meteorological condition from the quality signals that the cell towers are? I don't know whether they're tracking anything. Okay.
I don't think so. But what they are talking about is this system currently is homogeneous in the set of sensors.
Okay.
But when they're going to go to Houston, they're going to put in other types of meteorological data.
Yeah.
And then it comes very nice. The Blackboard then becomes a very nice system for having these shared perspectives and using that and integrating that information. So that's what I believe is the hope of the project, is to go to a heterogeneous thing, to build it out, to apply these ideas to multiple applications, and hopefully have an architecture that will be able to be easily configured for other applications. I don't know.
So have you thought about extending this to settings like crowdsourcing, where where there might be a large number of autonomous parties? Maybe everybody with who owns a building or a house could have a sensor on the top, and they might have, and then they might have vested interest in having their favorite phenomena or the flooding in their area recognized before anybody else's flooding is recognized.
Well, there actually exists, and I don't know, a public network of people connecting in their meteorological data into the thing. But that meteorological data is not, the sensors are not that great. That's the real problem. And the other thing is they aren't adaptive. So basically what we're doing is adapting the sensors. So in fact, if down the road, if there are better sensors that people want to put in their houses and they're adaptive, then yes, this would be something that could be used to, in some sense, get micro weather much better.
Zeroth order sensor is your roof still there?
Yes?
I'm sorry, I think I might have missed it, but does this work on heterogeneous sensors? Like,
The what?
Does it work on, or does it require that sensors be homogeneous, as in same power level, and
Well,
or does it?
this project